Let's say you as a scientist have been able to model the work done by heart as a function, as a multivariable function of the parameters, the average blood pressure, the volume pumped by your blood in that unit time, the density of blood, the average velocity of the exiting blood, and the acceleration of gravity of wherever you are. Now you want to analyze how this work changes as you change the various parameters, as you change the various variables. And the best way to do that is by taking partial derivatives. So let's start by taking a situation that you're on Earth, and on Earth the acceleration due to gravity is roughly 10 meters per second squared. And you take a rocket, let's say that's roughly a rocket, I don't know, and you reach a point A in space, where the acceleration due to gravity is 8 meters per second squared. And you continue moving from there. But what happens, what sort of change happens as you change g, as you change the acceleration due to gravity at these 2 points, on Earth and on the point A? So for that, let's take the partial derivative of work with respect to g. So you're essentially taking del over del g of the expression pv plus v delta v squared over 2g. Now, as you're taking a partial derivative, all other parameters would be considered as a constant. So since p and v are constant, their product is also a constant, so its differential derivative is just 0. In the second part of this expression, this entire blob that I have highlighted in white is also a constant, so you can just write it as it is. So v delta v squared over 2, and now you are left with del over del g acting over this partial derivative, acting over 1 over g. Now that is just this entire stuff is just equivalent to taking the single variable, the normal derivative of 1 over g with respect to g, and that we know is minus 1 over g squared. So the work done changes as we put a differential change in the acceleration due to gravity dictated by the equation minus v delta v squared over 2g squared. So a couple of things you can note from here. First, as you change g, as you increase g differentially, as you increase g in a really tinsy binsy nudge, then the work that your heart has to do decreases according to the following expression. Since there is a negative sign, and all other terms in this expression, volume is going to be positive, density is always positive, v squared is always positive, 2 is positive, g squared is also positive. So that means increasing g differentially decreases the work that your heart has to do differentially as well, according to the expression, by the way. Next, let's try what happens as you increase or decrease g at g equals 10 meters per second squared. So essentially, I'm taking the situation when the rocket's just at the Earth. So in this situation, in the situation of leaving the Earth into outer space, you're essentially decreasing g, and we will come to that point. But let's first evaluate the expression. So whatever that expression would be, we can just take this entire purple pink blob to be just a constant. Let's name it as b. So you would be left with minus b over 10 squared. Fairly good. Now, if you do the same for the point A, that we are considering in outer space, where g is equal to 8 meters per second squared, in that case, it would be minus b over 8 squared. So if you analyze it, then if you increase g somehow by at the position on Earth from where you're launching, your work changes by this much. And if you change g at 8 meters per second squared, the point in the outer space, your work changes by this much. We can also talk about some other parameters. Let's talk about average blood pressure. So now what you want to do is you want to partially differentiate the entire expression with respect to p. That was a capital P, I guess. So PV plus V delta V squared over 2G. I guess that was the expression. Okay. Now, again, except p, all the other variables are just a constant. So this entire block is just constant. And if you differentiate a constant, again, that is just 0. So you're essentially left, this problem reduces to being del over del p of pv. And since v is again a constant, so this can be written as v times del p over del p, which is just 1, so v. So now you know that if you increase the average blood pressure of the blood that your heart has to pump differentially, then the work that your heart has to do, the rate of change of the work that your heart has to do is the volume of the blood that it pumps out. So hopefully this accounts for a nice application of partial derivatives, and I'll see you in the next video.